So the topic of today is a continue a topic of the feedback amplifier. Uh, so we have finished the fundamental of feedback. We know all of the basic transfer function and how uh, we can calculate the overall closed loop gain from the open loop gain, right? So in this lecture, we will go through different. Actually, we will go through one specific topology or configuration of the feedback amplifier circuit, which is called series-shunt. So the ideal feedback topologies, there are four different types of topology, and these topology are based on the type of input to be amplified, so either voltage or current, and the output type, either voltage or current. So the first type of topology is called the series shunt. Second type is shunt series. So what is so let's pause here before we go through the last two. For series shunt, okay, the easy way is this. For series shunt, you have series, basically the series input give you a voltage input, the shunt output give you a voltage output. Therefore, the series shunt configuration would amplify from voltage to voltage. The shunt input would give you a current input, then the series output would give you a current output. Therefore, this would be some kind of like a current amplifier. Then we also have series when output is current and input is voltage. And we also have shunt when output is voltage and input is current. So as I say, the first one, since in output is voltage and input is voltage, this is a voltage amplifier. For shunt series, this is the current amplifier. For series, since this is a current, um, this is a current, output is current and input is voltage. This is a transconductance amplifier. And for shunt is also called a trans impedance. Sometimes you can say a trans resistant. Okay, so trans impedance amplifier. So in this lecture, we will focus on the series shunt configuration. So with the series shunt configuration, okay, first of all, let's pause a little bit. You can see that we have the main two port network. Okay, the first two port network is here. The second two port network is here. The first two port network is your basic amplifier. Okay, you can either use you can use a BJT or an op amp, or you can use a MOSFET. It's up to you. And the second this two port network is your feedback network. Okay, so since these are the two port network, I can represent this two port network with a small equivalent signal like this. I mean, small signal equivalent model like this, right? So in this model, I will have Ri would be equal to would be the input resistance of the basic voltage amplifier. I would have AV is the open loop gain, okay, of the basic voltage amplifier. Uh, I would have R naught would be the output resistance of the basic amplifier. So if you look at this in here, this is the reason why in most of the BJT amplifier practice that we do, we trying to figure out what is the input resistance and the output resistance, because later on when you build a feedback, you actually need this value to for your calculation later. Okay, so the next value is RIF, which is the input resistance of the whole feedback amplifier, and ROF, which is the output resistance of the whole feedback amplifier. I have beta V here, which is the voltage feedback transfer function. Okay, so if output voltage is amplified from arrow voltage via the open loop gain, I can have uh, out VO equal AV multiplied by VE. Okay, this is from the basic amplifier gain. Um, the feedback voltage provided from the output voltage via feedback network can be calculated at VFB equal to beta V multiplied by V naught. So if the source resistance is negligible, so if you use an ideal source, the RS will go to 0. Then the arrow voltage can be calculated as V epsilon equal to Vi minus VFB. Now calculate the overall closed loop gain. That would be AVF, which stand for closed loop gain, would be equal to output over input, right? So you can replace the output with AV, uh, AV and V epsilon in here. Okay, then you can replace V epsilon with Vi minus VFB. Then you replace VFB with what to do, you replace VFB with beta V naught. Then you can have this. Of course, like the Vi and Vi cancel out on these terms. So finally, you can see that uh, VO over Vi is AVF, so you replace that with AVF. Now you have an equation of AVF equal AV minus beta V multiply AVF. So you can solve this whole equation for AVF, right? So if you use that, you would have AVF equal to AV over 1 plus beta V AV. Now if you want to find the input resistance including feedback, that would be RIF equal to VI over II, so input voltage over input current. Okay, the input voltage is gonna be, you can use this equation to figure out. So arrow voltage plus feedback voltage over input current. Replace the feedback voltage with beta V naught. Then replace V naught with AV V epsilon, so amplify of the arrow voltage. So now you know that you can, if you know that the input current can be defined at V epsilon over Ri, which is the arrow voltage over the input resistance of your basic amplifier. You can replace that in here, then you can cancel out the arrow voltage to come up with an expression of RIF equal to Ri multiplied by 1 plus beta AV. Okay, let's pause a little bit here. So do you remember this term 1 plus beta AV from previous lecture? Basically, beta is usually large, right? I mean, it depends. It depends. Sorry, depend. Beta it depends, but A is pretty large. Okay, like A is pretty large. Then what happened is 1 plus beta AV is gonna be a large number. So if I have if I have beta equal 0.2, but AV equal to, let's say, 10 to the fifth, then this one is still a very large number. Therefore, one of the thing in series shunt is that when the input resistance is gonna be increased by a factor of 1 plus beta AV, depending like when you want to calculate the input resistance of the whole feedback circuit as a whole. Okay, so if you want a large input resistance, then you want to use Series-Shunt. Okay, now if this is a small signal equivalent model, okay, but with I replace the output with Vx so that I can calculate the output resistance, and it's gonna be Vx over Ix, which is the current flow in this direction. So the output resistance with feedback can be calculated as R naught ROF equal Vx over Ix. So if I analyze on this loop here, okay, I can have arrow voltage plus feedback voltage equals 0, and this is because of this is due to Kirchhoff voltage law. So I can have V epsilon equal to minus VFB. Some of you may ask, why do we eliminate the input voltage here? So when you, it's a good practice when you want to calculate your output resistance, you basically ground, you set your input voltage to 0. Okay, so let's continue in here. Since we have arrow message equal to negative VFB, which is the feedback voltage, the feedback voltage can also be calculated as beta Vx, because now in this case I replace VO with Vx, so arrow message will be negative beta Vx. Now if I analyze this loop in here, I can have Vx, okay, I start with this position, use the same Kirchhoff voltage law. I have Vx equal to the voltage across this resistance, which is Ro or R naught multiplied by Ix plus AV multiplied by V epsilon. So I can calculate my Ix, which is gonna be equal to Vx minus AV multiplied by minus beta Vx over R naught. So then you can multiply this minus sign out here to make it a plus sign, right? And okay, so you can now substitute this whole term for Ix in here. So top you have Vx, bottom you have Vx. Then you can simplify your expression for ROF to be this. Now take a look. Let's compare the difference between this equation and this equation. This equation, in order to calculate the input resistance with feedback, you basically multiply your basic amplifier input resistance for 1 plus beta AV, which make the input resistance overall larger. However, when you calculate the output resistance, you divide the basic input resistance, you divide the basic output resistance RO for 1 plus beta AV. Therefore, it makes the overall output resistance with feedback smaller. So if you have an application that requires a large input resistance and a small output resistance, then Series-Shunt is your choice. Now a new equivalent feedback circuit. So you can have you can basically write your whole network as one single equivalent feedback circuit like this, with input resistance gonna be the new RF here, and the output resistance is gonna be the new ROF here. Vi prime is basically gonna be depending on your how can I say this? Vi prime is gonna be depending on your source resistance. So if the source resistance is 0, ideal case, Vi will be equal to Vi prime. But if you present some imperfection in there, then you need to use voltage divider law to figure out what is the effective Vi prime that is applied on your feedback amplifier. Here's some summary for the series-shunt configuration. Input is going to be voltage, output is also going to be voltage. The transfer function of the feedback amplifier or the closed loop gain is going to be AV over 1 plus beta AV. The input resistance is going to increase and it's going to be multiplied for a factor of 1 plus beta AV. The output resistance will decrease by a factor of 1 plus beta AV also. Okay, so there are two different ways to represent or to implement series shunt configuration. The first one is to use op-amp representation. So this is a non-inverting op-amp series shunt feedback circuit. So as you see, this I use an op-amp, and the op-amp is gonna acting as your basic amplifier, and the feedback network is gonna be consisting of R2 and R1. So in the ideal feedback circuit, the amplification factor AV is gonna be pretty large, right? So if I have um, this is the closed loop gain of my overall feedback amplifier, and if I know that AV is large, then if AV is large, then beta AV is gonna be way larger than 1, right? Then I can basically simplify that. I can cancel out the term number 1, then I can cancel out the AV on the top and on the bottom, so I can estimate my AVF to be 1 over beta V. Oh, okay, so what are you doing there? Okay, so the gain of the non-inverting op-amp amplifier can also be represented as AVF equal to 1 plus R2 over R1. This is okay. This is referring to chapter 9, so you can go back to that. But now, if you combine this equation and this equation, you can set beta equal to 1 over 1 plus R2 over R1, right? So this now you can calculate your beta for this branch. Okay, so now I have I can have the small signal equivalent of this op-amp in here, like this. So I have an input resistance and an output resistance from the op-amp. I know the gain of the op-amp. I can define my error message and everything. So if we assume that IR is large, this is the super ideal case. If we assume that Ri is large and Ro is very small, then we can have uh, our feedback voltage is gonna be R1 over R1 plus R2 multiplied by VO. Therefore, we can calculate the overall, what's that called? The overall feedback, the overall closed loop gain to be AV plus 1 plus AV over 1 plus R2 over R1. To basically, I just plug in that beta there. So the input resistance will be RIF. Okay, so this is for the case of let's say you don't have a perfect RI or a perfect RO. The input resistance can be found as VI over II, so do the same way, but basically you multiply this RI for 1 plus beta AV, it's gonna be equal to RI multiplied by 1 plus beta, 1 plus AV over 1 plus R2 over R1, so I replaced beta with 1 over R1, 1 over 1 plus R2 over R1. So for the output resistance, you can do the same way, replace this beta with these terms. Another way to represent uh, Series-Shunt is to use discrete circuit representation. So these are examples of discrete transistors series-shunt feedback circuit. So this is an emitter follower circuit. This is using BJT. This is a source follower amplifier. This is using MOSFET. And here is the small equivalent of the emitter follower. So if in this case, error signal will be the base emitter voltage, or it's gonna be the gate source voltage. Since the output voltage, if you see in here, for both cases, the output voltage is exactly equal to feedback voltage, right? So the transfer function in this case is gonna be 1. Okay, so how can we find all of the closed loop gain and input and output resistance of the feedback amplifier circuit for the discrete representation? So first of all, we start with the output signal, and it's gonna be VO equal to RE multiplied by IE. So look at this loop in here. So we have VO, right? It's the voltage across this resistor. So technically, it can be calculated using Ohm's law. I'm gonna define a current going through in this direction, top to bottom. It's gonna be IE. Then I can have VO equal to RE multiplied by IE. This IE is gonna be the current coming out from top to bottom here. It's gonna be equal to two different current that coming in. The first current is the current going through the resistor R pi. So look at my pointer in here. And that is going to be equal to V pi over R pi. The second current is the independent current source GM pi. Now you can do some manipulation to get factor out V pi. Then you can have output equal to RE multiplied by V pi multiplied by 1 over R pi plus GM. The input signal. Okay, let's start with this loop first. You can have the input signal, you do the loop analysis. Okay, it's gonna be equal to V pi, right? Plus VO, or you can use directly RE multiplied by RI. You know this term already from this equation here. So technically just plug the whole thing in. Okay, now you have V pi plus RE, V pi 1 over R pi plus GM. So if you factor out V pi, you can have this. Now for the small signal voltage gain or the closed loop gain, just divided the output for the input. You can cancel out V pi. Now you have this. Now since these terms are quite are similar on the top and the bottom, right? You can define this term as small r, small e. Okay, small re, and small re is going to be r pi over 1 plus gm of pi. So the open loop voltage gain will be 1 over r pi plus gm multiplied for re, or it's going to be re over small re. The closed loop input resistance, or the input resistance with feedback, is going to be RIF equal to R pi plus 1 plus HFE, and this is in the H parameter, multiplied by RE, or in other words, it's going to be R pi multiplied by 1 plus RE over small re. And the closed loop output resistance will be RO equal to RE parallel with small re, and repeat this. So if we go through one design example, okay, if you are asked to design a feedback amplifier to amplify the output signal of a microphone, as the output signal from the microphone is going to be 10 millivolt, and the output signal from the feedback amplifier is going to be 0.5 volts. So you have to amplify from 10 millivolt to 0.5 volt. Okay, so you need this so that you can drive the power amplifier that turn on the driver in the speaker, blah 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 blah. The nominal output resistance of the microphone is Rs equal to 5 kilo ohms. So this means your source resistance is gonna be 5 kilo ohms. The nominal input resistance of the power amplifier is gonna be 75 ohms. So this is gonna be your load resistance, because you connect this feedback amplifier to a power amplifier. So given that you have an op-amp with some spec in here, the input resistance of the op-amp is going to be 10 k ohm. Output resistance of the op-amp is going to be 100 ohms, and the low frequency gain is going to be 10 to the fourth. Here I give you the small signal equivalent circuit of using the op-amps. The first thing you should notice is that the source resistance is quite large, right? It's 5 kilo ohm. It's not like a few ohms or a few milliohms. So with this large source resistance, you actually, when you design your amplifier, the input resistance of the amplifier, or the RIF, need to be very large so that you can reduce the loading effect at the input. So this number have to be a lot larger than this number. And also the load resistance is very low. Okay, it's 75. You now need a low output resistance. So this number need to be small in comparison to this, so that you can minimize the loading at the output. Okay, so now first question, every amplifier has a gain, right? How can you define how much gain you need for this feedback amplifier? Sorry, I missed one animation here. So the conclusion of that is, since we need a large input resistance and a small output resistance, then we need to use the series shunt. So now we come back to figure out what's the gain, what is the necessary gain for our feedback amplifier. We know that the input is going to be 10 millivolt. We need to amplify it up to 0.5 volt. So you just have to divide 0.5 volt over 10 millivolt, and it's going to be 50. So in ideal case, the feedback transfer function is going to be beta equal to 1 over AVF, and it's going to be 0.02. The loop gain is going to be T equal to beta AV, which is going to be 200. The input resistance is going to be RIF equal 200, 2 mega ohms. And the output resistance is going to be ROF equal to 0.5 ohms. So now you can see this 2 mega ohm is way larger than 5 kilo ohms, and 0.5 ohms is a lot smaller than 57 ohms. So in this whole circuit here, what can you do to design? I mean, what parameter do you have to change to meet all of this value? So in here you only have control over, because this one is given, right? You cannot change in here. So you only have control over R1 and R2. So if you can find R1 and R2, or at least a ratio between R1 and R2, you can finish the design. So, and that would be, you know, beta, right, from this design specification. So you know beta. You also know that since this is an op amp, you can have 1 over beta equal to 1 plus R2 over R1. So you can calculate R2 over R1 to be 49. So you can pick whatever R1 and R2 that you want to make this ratio happen. So that's it for today. In the next lecture, we will cover stability of feedback circuit. I hope you guys all learned something new, and I will see you guys next time. Bye.